Now consider a system of discrete charges, say Q1, Q2, Q3, Q4, Q5, such that the charges Q1, Q2 and Q3 are inside the closed surface S, and the charges Q4 and Q5 are outside the Gaussian surface S. The resultant electric field strength E at any point will be equal to E1 plus E2 plus E3 plus E4 plus E5. The net flux of the resultant electric field strength E through the Gaussian surface is phi is equal to integral E dot dA, which is equal to integral E1 dot dA plus integral E2 dot dA plus integral E3 dot dA plus integral E4 dot dA plus integral E5 dot dA. Since charges Q4 and Q5 are outside the Gaussian surface, net flux due to these two charges is zero. Hence, the net flux on the surface is due to the three charges inside the Gaussian surface. That is, phi is equal to integral E1 dot dA plus integral E2 dot dA plus integral E3 dot dA. Therefore, phi is now equal to Q1 by epsilon naught plus Q2 by epsilon naught plus Q3 by epsilon naught. Or we can say that net flux through the Gaussian surface is equal to Q1 plus Q2 plus Q3 by epsilon naught. Let the total charge enclosed within the Gaussian surface be Qn. The subscript in referring to inside of the closed surface. Here, Qn is equal to Q1 plus Q2 plus Q3. Now the above equation for net flux can be written as phi is equal to integral E dot dA is equal to Qn by epsilon naught. Let this be equation 6. It is important to note that the electric field strength appearing in equation 6 is the net electric field strength E due to all charges present within the Gaussian surface and also outside the Gaussian surface. But the charge Qn appearing in the above equation is the charge within the Gaussian surface. In principle, Gauss law is used to calculate the electric field strength E due to a system of discrete charges or even a continuous charge distribution. From the above observations, we can look at some important points regarding Gauss law. Gauss law is applicable to any closed surface of any arbitrary shape. In the mathematical form of the Gauss law, we see that Qn is the sum of all the charges enclosed within the Gaussian surface, irrespective of their positions within the surface. The electric field strength appearing in the relation integral E dot dA is the net electric field strength E due to all charges present within the Gaussian surface and also outside the Gaussian surface. However, the charge Qn appearing in the above relation is the charge within the Gaussian surface. While choosing a Gaussian surface for a system of discrete charges, the Gaussian surface chosen should not pass through the system of the charges since the electric field is not well defined at the location of the charges, as it grows boundlessly as we move closer to the charge. However, in case of a continuous charge distribution, the Gaussian surface can be taken passing through the charge distribution. Symmetry is crucial to the application of Gauss law, since it makes the calculation of the electric field easier. Gauss law can be chosen to evaluate the electric field due to charge distributions that have spherical, cylindrical, or planar symmetry. Since Gauss law is based on the inverse square dependence on the distance contained in the Coulomb's law. Any violation of the Gauss law indicates a departure from the Coulomb's law.